Okay, let us solve the example. So in this case, we have a system with a relay. Okay, and relay has the magnitudes 1 and -1, and we have here system 1 over s, s plus 1, and s plus 2. So here, the task is to determine the frequency and the amplitude of the oscillations and there's another question: are the oscillations stable or unstable? Okay. Remember, we have learned about the stability of oscillations. So we are thinking about an oscillation as an equilibrium point, because when a system enters into an oscillatory trajectory, if a system enters into an oscillatory trajectory that is looking like this, it never goes out of that oscillatory trajectory. It is always also oscillating. So in some way, an oscillatory trajectory is like an equilibrium point. The system cannot escape from it once it is there. Okay? And similar to equilibrium points, which can be classified as stable or unstable, we could classify oscillations also as stable or unstable. Remember, when I have an equilibrium point, and if the trajectories of the system are pointing towards the equilibrium point, around an equilibrium point, if the trajectories of the system are approaching the equilibrium point, for small perturbations, then that equilibrium point is called actually a stable equilibrium point. On the other hand, if there are trajectories going away from the equilibrium point, in the vicinity of an equilibrium point, then such an equilibrium point is called an unstable equilibrium point. Similar to this, by using an analogy here, by the analogy of thinking about the oscillatory trajectory as an equilibrium point, we could actually define a stable oscillation or unstable oscillation. If the trajectories are going towards the oscillation, in the vicinity of oscillation, oscillatory trajectory, then we would actually call the oscillatory trajectory as a stable one. Okay, similar to an equilibrium point. And we could have the reverse behavior, in which case we would say that the oscillations are unstable. Describing function is used for both determining the frequency and the amplitude of the oscillations in a system approximately, and also we can determine the stability or instability of oscillatory trajectories by using describing function analysis. So here we won't calculate the describing function of this relay because we have already done that. Remember that if we have a relay with the magnitude A minus A here, this is EU, we have calculated the describing function and E hat omega to be 4A over pi E hat. Okay? This was the describing function of a relay. And now we could actually use this fact that we have obtained so far in writing the describing function of this nonlinearity. So here, in this case, A is equal to 1, okay, for this example. And that actually means that I could actually draw my approximate system. I will replace the nonlinearity by its describing function, 4 over pi E hat, okay? And then, here, the system is going to be kept as before. And that is my approximate system. So now, for the sake of simplicity, sometimes I would call the describing function as k. So it's a good way to confuse students. So k, n, or 4 over pi E hat. We have many names for the same thing. So here, let us try to write the equation for this system. 1 plus k, I could write s cubed plus 3s squared plus 2 is equal to 0. This would determine the closed loop poles. And I have s cubed plus 3s squared plus 2s here plus k is equal to 0 here. This is the equation determining the closed loop poles. And what I need here is that at s equals to j omega, I would need closed loop poles for the oscillations to happen. Okay? And let us substitute s equals to j omega minus j omega cubed minus 3 omega squared plus 2j omega plus k. Here k is real. Sometimes describing function can be complex. In that case, you have to consider that the k is going to be a complex number. Okay? But here k is real. So that actually means that it's going to go into the real part of this equation. Let us collect the real parts. K minus 3 omega squared is equal to 0. And in j omega parentheses, I have 2 minus omega squared is going to be equal to 0. Okay. From this equation, I get omega is equal to 0 and omega squared is equal to 2. So omega is equal to plus minus square root 2. Okay. And I have here k is equal to 3 omega squared. Omega is equal to 0 is not really an oscillation. It's a DC term in that case. So I will neglect this solution. Instead, I will concentrate on this omega squared is equal to 2. And in that case, k should be equal to 6. Okay. So here we can k is equal to 6 is going to give me 4 over pi e hat. And in that case, I could calculate what e hat should be. It's going to be 2 over 3 pi. Okay, from this equation. So when there are oscillations, the amplitude of the oscillations would be looking like this. It's going to be approximately 2 over 3 pi. And the frequency of the oscillations, we are expecting them to be square root 2 radians per second. So here this will complete the task of finding the frequency and the amplitude of the oscillations when there are some. And now we're going to concentrate on the case of the stability, determining the stability of the oscillations. So in this case, if I substitute that e hat here, I'm going to get k is equal to 6. So we see that k value is a positive real number. Okay? And in that case, we know that if this describing function was not here, I could actually have drawn a root locus for such a system, where the closed loop poles are. Okay? The answer to that question is the root locus. So that is why I'm going to be drawing a root locus for the system for different k values. When k changes from 0 to infinity, we're going to draw the root locus, and the root locus is going to give us the characteristics of the closed loop poles of this system. And at k is equal to 6, we know that that root locus is going to intersect the imaginary axis. Okay? So here I will draw the root locus onto the complex plane. Root locus'ta ne çizeriz? Çizdiğimiz şey nedir? Which poles? Closed. Bunlar klasik master giriş sınavı. Sözlü soruları. Lineer sistem nedir? Linearity nasıl tanımlar? Söz alıyor genellikle. Tahtada işte root locus falan sorulabiliyor. Nyquist sorulabiliyor. Bode plotunu çizilebiliyor. Öyle şey. Yani bir 5-10 dakikada bitmesi lazım çünkü 15-20 öğrenci aynı anda mülakata girecek. Artık yaratıcılığı insan bir yerden sonra kaybetmeye başlıyor. Çünkü içeriden çıkanlar hemen dışarıdakilere soruları anlatmaya çalışıyor. Çok iyi kalplisiniz gerçekten. Hayır, farkında değil ki. Ondan sonraki o soruyu bilirse zaten onun yerine master programı gelecek. Okay, let us try to draw the root locus. So I have an open loop pole at 0, -1, and -2 here. And I will fill in the real axis parts. Here I would fill in the real axis parts. The total number of open loop poles and zeros to the right should be an odd number. So I have here, these parts should be filled. Put some arrows going away from open loop poles and towards open loop zeros. And then I need the asymptotes. The intersection point of I need 3 asymptotes here. So I will find the intersection point of the asymptotes. I will sum the poles, -3. Minus zeros, it's still minus 3 divided by 3. The asymptotes are intersecting at the point -1. Okay? And the asymptotes will have 60 degree, -60 degree, and 180 degrees angle. So these are the 4 rules of the root locus. So this much you have to understand understand root locus in this course. Okay, so you have to know how to draw the root locus in this way. So then if I draw the roots, then I'm going to see that it is going to be looking like this. So now I can ask you the following question: what is K here? What is K here and here? K is 6 is here, and what is this point? This is j square root 2, and this is minus j square root 2. Okay? So now so this specific K value is actually 2 pi, it is 4 over pi I e hat. Okay, that is what we have. If I call this e hat value e hat star, okay, then this is going to be 4 over pi e hat star. Okay, that is what I have. So now I'm going to think about the stability of the oscillations. I will show a oscillatory trajectory that is looking like this. This is just the figure that I made up. Okay? I assume that E is the x-axis of this plot. So I see that as the system trajectory is rotating on this curve, E is going to make some oscillation. Okay? So E is going to have E hat sine omega t type of periodic motion. As the trajectory of the system turns around on this trajectory, the x-axis value of this trajectory is actually going to make a sinusoidal or almost sinusoidal motion here. Okay? So here let us try to look at the following. Suppose that I increased E hat above the value E hat star. Okay? If I artificially increase the amplitude of the system on this oscillation, amplitude of the signal E, artificially, if I increase it artificially to pull the system trajectory outside this oscillation, okay? In that case, I would increase E hat, okay? Above the value E hat star, okay? If E hat star is actually increased, what is going to happen to this gain K? It's going to be decreased or below the value 6, or it's going to be increased above the value 6. What can you say? In this case, we see that if E hat increases, then K is going to be decreasing. Okay? What would happen in the root locus if K is decreased? In that case, what can you say? If K is decreased, the closed loop poles are going to be drawn to the left half plane. Okay? In that case, what can you say about the closed loop stability? If K is smaller than 6, what can you say closed loop stability? It is stable. Stable closed loop system. If a closed loop system has poles in the open left half plane, what can you say about the magnitude of the oscillations E hat? What can you say about E hat? They will decay exponentially. Where are they going to decay towards? They will decay towards the value E hat star. Okay? That is what is going to happen. So we see that the internal dynamics of the system is going to pull E hat back to its original oscillation value E hat star. Okay, that is what is going to happen. So on the other hand, if I decrease E hat, okay, then K is going to be increased. If K is increased, the closed loop system is unstable. And then the closed loop system is going to have closed loop poles in the right half plane, meaning that the oscillation amplitudes will grow by the internal dynamics of the system. Okay? And that is going to pull back E hat to its original value, E hat star. Okay? So that means that if I start the system somewhere here outside the oscillation, E hat star is going to come back to its original value. On the other hand, if I start the system somewhere inside this oscillation, E hat is going to grow to pull back the value of E hat back to its original oscillatory value, E hat star. Okay? So what can you say about the stability of the oscillations for this system? They are stable. So we have stable oscillations given by the describing function analysis. Mm-hmm.
Yani bu tanım neyden dolayı? O tarafa kayıyor mesela. Left half plane'e kaydığında stable diyoruz. Right half plane'e kaydığında stable diyoruz. Ama günün sonunda İHAT kaynağına göre ayarladığı için sistemi stable.
Şimdi bir sistemin sağ tarafta polları olduğunda sistem unstable oluyor. Böyle kompleks pollar olduğu için E hat büyüyecek diyorum sistemin internal dinamikleriyle. Tamam mı? Sadece E hat'in büyüyeceğini mi küçüleceğini mi? Sistemin internal dinamikleriyle E hat büyümeye devam mı edecek yoksa küçülmeye mi çalışacak? Ona bakmaya çalışıyorum. Ben E hat'i artificial olarak yukarıda bir değere çekersem sistem onu geri getirebiliyor mu kendi internal dinamikleriyle? Ona bakmaya çalışıyorum aslında. E hat'i artificial olarak yukarı çekmek sistemi oscillation'ın dışına çıkartıcı bir şey. Ben bunu artificial olarak dışarı çekersem o zaman sanki sistemdeki gain, describing function düşmüş gibi oluyor. O düştüğünde de sistemin closed loop polları, ben imaginary eksende polları olmasını istiyorum sistemin. Ben artificial olarak sistemi osilasyondan çıkarttığım zaman o durumda closed loop sistem stable hale geliyor. Ve de E hat sistemin dinamikleriyle düşüyor o artificial değerinden. Yani şu yukarıdaki değerinden geri düşmeye çalışıyor sistem otomatik olarak.
Yani bizim o stable dediğimiz durum İHAT kendi düşecek demek.
Evet. Aynen öyle. So I'm trying to now solve the same example, the same linear system. But instead of actually putting a relay here, I will put a saturation element. Okay? So I will have a saturation element. And here, the slope of the saturation element is going to be K. Okay? And here, these threshold values, so this is not saturation, this is dead zone, sorry. So I will put a dead zone element here. And in this dead zone element, the dead zone is between -1 and +1. And the slope of the dead zone element is actually K. And in the previous lecture, we have actually calculated the dead zone element describing function. When E hat is smaller than or equal to 1, we get 0. And when it is larger than 1, in that case, we calculated the following. So I have pi sine inverse 1 over E hat minus 1 over E hat, 1 minus 1 over E hat squared. We calculated this describing function in the previous lecture. Okay? That is my describing function. And if we could draw this describing function, it is actually be looking at as follows. So I have E hat here, and here I have n of E hat. Describing function is 0 until E hat hits 1, hits the value 1. And then it goes to the value k. Okay? This value is k. This is small k. It's different than the capital K that we use. So now in the question, we're going to look at the following. Determine the existence and stability of the oscillations for k is equal to 1 and k is equal to 10. Okay? When this small k changes, in one case it's going to be equal to 1, and in the other case, in the other case it's going to be equal to 10. So now if I draw my approximate system here, so I will have capital K is equal to the describing function n of E hat, okay? And here I will have my system 1 over I have s plus 1 and s plus 2, okay? So I have this system. And here I have the describing function, which is shown as a simple gain k, okay? I know that such a system is going to have poles on the imaginary axis if k is equal to 6. Okay? If k is equal to 6, then I will have S12 is equal to plus minus j omega, where omega is square root 2. Okay? I will have poles of this system if k, or if the describing function is exactly equal to 6. And in that case, I will have closed loop poles at these two locations. That is what we have already drawn there. So now I'm going to be looking at the two different k values. For k is equal to 1, let us try to draw the describing function. It is 1 here, and here for k is equal to 1, the maximum value of the describing function, or its supremum, is going to be k, small k is equal to 1. Okay? In this case, I want this describing function curve to intersect capital K is equal to 6. Okay? This is k is equal to 6. So then the question is, what can we say about the existence of oscillations and their stability? In this case, do you think we will have any oscillations in the closed loop system? This describing function can never be equal to 6. Okay? In this case, that actually means that for any E hat value, I will not have the solution of a harmonic balance equation. Okay? That actually means that in this case, we have no oscillations are expected in the system. What about the other case? So the case when small k is equal to 10. In this case, the describing function curve is going to be looking like this, and I have 10 here, and 1, and I have E hat. Okay? And now k is equal to 6 is looking like this. So this is capital K is equal to 6, and this is small k is equal to 10. In this case, do you expect oscillations in the closed loop system? Yes, there is actually a solution of the harmonic balance equation, and that is going to be just this solution. Okay? So here I'm expecting a solution. So I'm expecting an oscillation in the control system. So this specific value where this E hat is equal to the amplitude of the oscillation is going to be E hat star. Okay? How can I calculate E hat star? How can I calculate? I will try to solve, I will equate this equation to 6, and I will try to solve for E hat value that will satisfy this equation. Okay? So in this case, I can actually say that oscillations exist. So then the question is whether those oscillations are stable oscillations or unstable oscillations. Okay? Let us try to investigate. If I increase E hat above its value E hat star, okay? If I increase E hat above the value E hat star, what is going to happen to the gain K? K is equal to N here, which is the describing function. If I increase E hat, then K is going to increase. If K increases, what is going to happen to the closed loop poles? They will go to the right. It is increased above the value 6, and the closed loop poles will be in the right half plane now. Okay? So closed loop is unstable. If closed loop system is unstable, what is the internal dynamics going to do to E hat? It's going to make E hat even larger. Okay? So what is happening here? If I pull the trajectory outside the original oscillation, if I make the E hat larger than its oscillatory value, then E hat would get even larger by the internal dynamics of the system. So what can you say about oscillation then? If I make the system deviate from this oscillation, it's never going to come back to its oscillatory value again. Okay? So what can you say about this oscillatory trajectory then? It's going to be an unstable oscillatory trajectory. So now here is what I can say. Suppose that I put here another nonlinearity, and suppose that this nonlinearity has the following describing function. If this is E hat, and let us say that the nonlinearity has a describing function looking like this. Okay? Here the value is 6 this here. K is equal to 6. Okay? And this is my describing function n of E hat. I replace this term by a nonlinear function whose describing function is looking like this. Okay? Do you think oscillations will exist in the control system? How many distinct oscillations would you expect? How many distinct oscillations with different properties? 3. We will have 3 different amplitudes for different oscillations. So I have a single one here, another one here, and another one here. So what can you say about the stability of the oscillations? For each one of them, the conclusion might be different. Okay? For this one, do you think it's going to be a stable oscillation or not? This is unstable. This is also unstable. And this is stable. Okay? So there will be local properties of these oscillations. What does that mean? That actually means the following. So system might have 3 distinct limit cycles. Okay? So 3 distinct limit cycles with different amplitudes. Okay? The inner limit cycle is actually unstable. Okay? So meaning that the trajectories are actually getting away from this. Okay? And they are actually going towards the other oscillation here. Okay? So the trajectories of the system are actually looking like this. And the outermost one is also an unstable one. So the trajectories are getting away from this oscillation, but to this one we have convergence. Okay. So the system trajectories would be actually looking like this. We do not solve any differential equations. We just linearize the nonlinearity. Okay, but in this case it is in frequency domain, and we could draw a pretty good picture of how the trajectories of such a nonlinear system would be looking like. Okay. So one more example. This is the nonlinearity. This point is E hat, and this point is minus E hat. So I have EU curve here. And I have U of t here. And I have the following system. 1 over S plus 1, S plus 4. Okay? So I have this. The question is the same. Okay? So I have to determine the parameters of the oscillations, if any, and determine the stability, if it is possible. So here, I will remind you the hysteresis relay example here. Okay? So this was my here is the relay with hysteresis, and at this point was B, minus B, A, and minus A, and E hat was somewhere here, and this is minus E hat. This is relay with hysteresis, and we have actually found its describing function, n of E hat, as 4B over pi E hat, times I have 1 minus A over E hat squared, and I have A over E hat J. So it is for this. So this describing function is for this component. Okay. Now what I want is that I want this element to work like this. Okay. So I want this A and E hat to be the same point. Okay. So we know that this has actually counterclockwise rotation that is looking like this. We want these boundaries, these A boundaries, to come to E hat. Okay? So here, that is why I'm going to be selecting here A to be exactly equal to E hat. Okay? To find the describing function of this nonlinearity. Okay? So here, when I make that selection, this is actually going to make one, and this term is going to cancel. All right? And I see that the describing function in that case, with that selection, is going to be minus 4b, and here maybe I have the amplitude 1 and minus 1. Okay? 1 and minus 1 here. And that is why I will choose b is equal to 1. Okay? So the describing function here is going to be minus 4 over pi E hat J. Okay? I get this. So now let us look at our approximate system. Okay? The approximate system is actually looking like this. So I have K is equal to minus 4J over pi E hat, and I have my system 1 over s plus 1, s plus 4 here, and this is my approximate system. Okay? So now let us try to look at the system. So I have 1 plus k, 1 over s squared plus 5s plus 4 is equal to 0. Okay? And that is going to give me s squared plus 5s plus 4 plus k is equal to 0. Okay? And then I have substitute j omega here, minus omega squared plus 5j omega plus k plus 4 is equal to 0. Okay? I would get this. Now collect the real and imaginary parts. K plus 4 minus omega squared is equal to 0. And omega is equal to 0 coming from the imaginary part. I'm making a deliberate mistake here, okay? Have you noticed? What happened?
K is complex.
Yes, K is complex. Okay? So I cannot really do this. Okay? So I cannot really continue collecting the real and imaginary parts in this manner. So I could actually here I have minus omega squared plus 5j omega plus, instead of k, I need to substitute that. Okay? Minus 4 over pi e hat j, and I have plus 4 is equal to 0. Okay? So this is going to give me the real and imaginary parts. 4 minus omega squared is equal to 0, so omega is equal to plus minus 2, and I would get in j parentheses 5 omega minus 4 over pi e hat is equal to 0. So here, what does this give to us? So 4 over pi e hat is equal to 5 omega. So I can write what e hat is. E hat is going to be 5 over pi, 5 pi omega. Okay? And I can substitute plus 2 or minus 2 here. So my signs are going to be plus minus 2 over 5 pi. All right? So I will get this. So will there be oscillations? Yes, there are solutions to the equation, harmonic balance equation. So I'm expecting oscillations. Okay? By the way, these two solutions are the same thing. Why is that? E is equal to E hat sine omega t. Okay? So I can write the same thing. In one of them, omega is equal to minus 2. And in that case, E hat is minus 2 over 5p. So minus 2 over 5 pi, okay, when it's minus 2. So I have sine minus 2t. Okay? So I have this thing. And the other one is E of t is equal to, I have plus 2 sine 2t, and I have 2 over 5 pi. These two things are the same thing. Okay? So any one of them, I can think about any one of them. They are the same thing actually. Okay? So here, let us check what is going to happen to the stability of the oscillations. Let me draw the slopes. Where is my solution? This is not intersecting the imaginary axis. What is going on? I needed to have a solution with the imaginary axis. Otherwise, I won't have an oscillation. But I have found a solution to that equation. What is going on?
Is it because K is complex, so K also has an S term and there's a 0 to
Yes. Yes, exactly. This thing is complex. Root locus is drawn for real K values. Okay? So I cannot find the solution with regular root locus. Okay? So in this case, a reasonable way is to use the Nyquist plot for the same purpose. Okay? Because Nyquist plot allows actually complex gains as K. Okay? But I will not do it that way. Okay? It is because the Nyquist plot, although we teach it in 302, the performance of I think it's too early for Nyquist plots. I think Nyquist plot is more like a graduate topic. It should be a graduate topic. So in my opinion, so every time I taught Nyquist plot in this course, I was really very, very disappointed. So I'm not removing Nyquist plot from this course because of you. I'm removing it because of me. I don't want to question my life choices and my profession or anything like that. I believe that Nyquist plot belongs to graduate study. Okay? So that is why we are not going to be using the Nyquist plot, and I will not be asking questions related to the Nyquist plot. But here there is a way actually to solve this question without using the Nyquist plot. Okay? And the way is actually going to be the following. I will take this thing, minus 4 over pi e hat, okay? And I have a j. We know that j omega is actually s, okay? So here is what I'm going to do. I'm going to write omega here, and I will divide it by omega, okay? Then what does happen to this? Minus 4 over omega pi e hat times s. I can take S into the system. Okay? That is what I can do, and I can draw the root locus. Can I draw the root locus? In that case, the gain is negative. For negative K, we have something called complementary root locus, but I will not be asking from you that one either. It is an undergraduate topic, in my opinion, but I will not ask for that either. I will try to do something better now. It's minus 1. I will put a cube here. Okay? I will put a cube here. And then what is going to happen? This is going to be s cube plus. Okay? So then I will take this s cube into the system. And I will draw the root locus for positive k values. Okay? But that's going to be next week. That's all for today. Thank you.